In this video, we are going to solve a sample problem regarding unsteady-state conductive heat transfer. The problem reads, a billet of steel, 30.5 centimeters in diameter, 61 centimeters long, initially at 645 Kelvin, is immersed in an oil bath that is maintained at 310 Kelvin. If the surface conductance is 34 watts per square meter per Kelvin, determine the center temperature of the billets after 1 hour. Now, what gave it away that this is an unsteady state conduction problem? Well, we have certain keywords such as the words initial and final. And whenever you have a parameter of time, that means that you're dealing with an unsteady state problem. This is very different from how we handle steady states, heat transfer due to conduction, right? Wherein we simply take a look at resistances in series and then determine the steady state rate of heat transfer. In this case, we have to do it very differently. Now, I have here on my cheat sheet right here the two dimensionless numbers that are very important for unsteady state conduction. We call them the Biot number and the Fourier number. Now, take note that the Biot number contains the convective heat transfer coefficient H, and then the Fourier number contains time. So, those two dimensionless numbers have different purposes. The Biot number can actually tell us if we would have an easy solution or if we would have a complicated solution. Let me explain. We have two types of systems when it comes to unsteady state heat transfer. We have what's called lumped systems, and we also have distributed systems. The difference between these two types of systems is simple. If you have a lumped system, the temperature is only a function of time. That means that my cylindrical billet here, if it's a lumped system, for any given value of time, the temperature is consistent in any part of the cylinder. There are no temperature, or we assume that there's no temperature differences between the parts of the cylinder if it's a lumped capacitance model. If it is a distributed system, the temperature is now a function of both position and time. I'm just using R here to pertain to the radial position inside of the cylinder. So a distributed system is very complicated because there are now two independent parameters: the position, the radial position, and the time. And whenever we have distributed systems, we do have several methods for that. You can have uh, both an analytical and a graphical solution for that. But let's just hope that this is not a distributed system. So how do we determine first if your system is lumped or distributed? That is where the Biot number comes into play. Take a look at the notes. The Biot number is calculated as H times V over A over K. The H here is the convective heat transfer coefficient of the fluid outside of the solid, and K is the thermal conductivity of the solid. It's very important to take note that the Biot number half pertains to the fluid, half pertains to the solid. Okay, so this K is for the solid. Now we are already given the value of the heat transfer coefficient. That's 34 watts per square meter per Kelvin. And I also have here listed for you the properties of a certain alloy of steel with the thermal conductivity of 16 watts per meter per Kelvin. So we can already calculate the Biot number. This is what we're going to use to classify if your system is lumped or distributed. If the Biot number is less than 0.2, we have a lumped system. Or that's a very simple statement, but the reality is if your Biot number is low, that means that there is very little error associated with assuming that your system is lumped, such that we can generally assume that it's lumped. But for higher values of the Biot number, you cannot assume that it's lumped because you would now have significant errors in approximating the temperatures in your system. So let's evaluate our Biot number. But notice first that we have here a volume to surface area ratio. For this cylinder right here, we can calculate that as the volume is simply pi over 4 d squared times L. That's the volume of a cylinder divided by the surface area. The surface area is divided into two terms. The first term is the lateral surface area of the cylinder right here. The second term is the surface area of the both ends of the cylinder, the top and the bottom ends. So for the top and bottom ends, that will be 2 times the area of a circle that's pi over 4 d squared, right? It's multiplied by 2 because you do have the top and the bottom surfaces. Plus the lateral surface area of the cylinder, that's pi dl. Since we're already given the diameter and the length, we can directly calculate for this volume to surface area ratio. Take a look at the calculator. Let's calculate. For the numerator, that is pi over 4 times diameter. I'm going to convert my diameter and length in meters, right? So my diameter is 0.305 meters squared. Sorry. Times the length, 0.61 meters. Divided by the total surface area. So that would be 2 times pi over 4 times diameter squared plus pi dl. I'm getting a value of 0.061 meters. Now keep in mind that since we are considering the entire surface area of the cylinder right here, the effective characteristic length, which is the ratio of the volume to the surface area, is actually quite small. It's only 6.1 centimeters, which is considerably small compared to the diameter of the cylinder and compared to the length of the cylinder as well. Okay? Now, this right here, when we substitute to the BU number, we can already calculate this one. So, go back to the formula of the BU number. That is H, or the heat transfer coefficient, times the effective characteristic length divided by the thermal conductivity of the steel. I'm getting 0.13 as my BU number. Now, 0.13 is less than 0.2, which is our common threshold for the characterization of a lumped system. But you do have to take note that for other textbooks or for other references, they are suggesting that the threshold for the BU number be lowered to 0.1. Because remember that there really isn't a very hard definition of what should be the BU number before you can consider the system lumped or distributed. It's a matter of looking at it in the point of view of how much deviation or how much error are we going to incur if we assume that the system is lumped. Okay? But for our purposes here, 0.13 is less than 0.2. We're going to consider this a lumped system. And if you have a lumped system, you are in luck because the formula for unsteady-state conduction is very simple. It's simply the unaccomplished temperature change, which would be equal to the exponential of negative BU number times the Fourier number. I already have the value of the BU number here. It's 0.129625. We're going to use that later. And I just need to solve for the Fourier number. And you just need to know how to define the unaccomplished temperature change. The unaccomplished temperature change in the numerator is simply the final temperature of your steel minus the surrounding temperature divided by the initial temperature minus the surrounding temperature. Let's take a look at the given. You're given the initial temperature of 645 Kelvin, right? That's your T sub I right there. And you're also given the surrounding temperature of the bath. It's 310 Kelvin. So imagine that your cylinder is hotter compared to the surrounding fluid. So the direction of heat transfer will be from the cylinder to the fluid outside. Now, the direction of heat transfer happens both in the radial direction and also in the axial direction at the same time. Because remember that there are no insulated sides to this. That means that every surface area that is exposed will be or will allow heat transfer. Okay? We are looking for the center temperature of the billets after 1 hour. So we are already given here our value of time. It's 1 hour. Now, notice that it was specified that we are to solve for the center temperature. that is where another very important difference between a lumped and a distributed system comes into play. For a distributed system, the center temperature after 1 hour is not the same as the surface temperature after 1 hour. It's also not the same as the temperature at this point, different from temperature at this point, this point, this point, and so on and so forth. But for a lumped system, the center temperature is the same as the surface temperature, is the same as the temperature for any other point inside of your cylinder. That's the beauty of a lumped system. Okay, so this final temperature right here already pertains to the temperature of the entire billet of steel. We can directly calculate it. But first, let's calculate for the Fourier number. Take a look at the formula here. The Fourier number is equal to alpha T over V over A squared, which we already have a value of, right? Now, what is alpha? Alpha is the thermal diffusivity of the system, of the solid. Now, alpha can be calculated as K over rho times Cp. That's conductivity over density over the heat capacity of your solid. This pertains to the solid, which is the steel. So I have here the properties of steel. All of these are already in standard SI units. We can directly substitute that in our calculator. That is 16 divided by 7,700 times 500. I'm getting a value of 4.156 times 10 raised to 6 minus 6. The unit of this is square meter per second. That's the standard unit of diffusivity. Whether that be momentum diffusivity, thermal diffusivity, or mass diffusivity, they all have the same units, right? So this is the alpha that you're going to use for the formula of the Fourier number here. But do not forget, when you substitute the time here, it's not supposed to be in hours. It's supposed to be in seconds, because take a look at your thermal diffusivity. It's expressed per second, right? So be very careful with your units. Let's substitute for the Fourier number, alpha times time. So 1 hour is equivalent to 3,600 seconds divided by V over A squared. Earlier, we calculated V over A to be 0.061, and we get the square of that. I'm getting a Fourier number of 4.02. Another reminder, the Biot number and the Fourier number are both dimensionless numbers. Dimensionless meaning they're not supposed to contain any unit once you have calculated them. So if you substitute all standard SI units, we can expect all of those to cancel out. Okay? Just be very careful when you substitute those. Now I'm going to recalculate my Biot number earlier, because remember that I just rounded it off to two decimal places, but we might incur a large error if we do that. So let me place more decimal places to that. So that's 34 times 0.061 divided by 16. That's roughly 0.1296. Let's use that. Now, of course, if you don't want any round of error, you can simply substitute the formula directly in our formula here for the unaccomplished temperature change. But nonetheless, using this formula, we're now ready to solve for the final temperature. And again, remember, since this is a lumped system, the final temperature applies to any point inside of the cylinder. Calculating that, you can use shift solve if you have that function in your calculator. But if you want, you can also perform the cross multiplication. So I can calculate that as surrounding temperature 310 Kelvin plus the difference between the initial temperature and the surrounding temperature. That's 645 minus 310 times the exponential of the negative Biot and Fourier number. Negative Biot times Fourier. This is now my center temperature after 1 hour. Let's round that up to 509 Kelvin. Now, always ask yourselves, does this answer make sense? My cylindrical billet of steel started at 645 Kelvin, and it's surrounded by a colder fluid, which is at 310 Kelvin. And we mentioned that heat is being transferred out of the cylinder, from the cylinder to the fluid. So it should make sense that the final temperature should go down, and it should be lower than 645 Kelvin. If my initial temperature is 645 Kelvin, as time approaches infinity, we can expect that the final temperature should approach the temperature of the surrounding fluid, which is 310 Kelvin. It's a principle of thermal equilibrium, right? Given enough time, your billet of steel will come into thermal equilibrium with the surrounding fluid. And assuming that your surrounding fluid is vast, meaning it has very, very large mass, then we can expect that its temperature will not change that much. So we can expect that the temperature of the cylinder approaches the temperature of the surroundings. Okay, that's it for this problem. I hope that you learned something from the Biot number to the Fourier number to the difference between a lumped and a distributed capacitance system. Thank you for listening, and I'll see you on the next one.